today we'll build up what we discussed yesterday, and in particular the idea is to clarify the connection between unitary ensembles. Yeah, it looks okay. Yes. So the connection between the unitary ensemble and the Toda lattice hierarchy, and in particular we will see how, when you consider the thermodynamic limit, the limit where the size of the matrices goes to infinity, the observables of the some of the observables of the theory, at least, satisfy an integrable hierarchy of equations of hydrodynamic type. As in the spirit of yesterday's session, we will see this in a concrete example, but actually want to anticipate that what we see is actually a more is a property that arises also when you consider all other random matrix ensembles. So yeah, perhaps in the seminar we will see like the next step and more recent results in this direction. Okay, so so we start from the idea that if you consider a random matrix ensemble of the Hermitian on the unitary ensemble, so the matrices belong to the space of the Hermitian matrices of order n, and then with a given weight, a given measure on this space, the partition function. Now we got used to denote it as tau n, which is the actual partition function up to a constant that depends on n, is equal to 1 over n factorial, the integral over Rn of the Vandermonde determinant squared times the product over I running from 1 to n of rho zi, function of the parameters t, where rho is just a function of the one variable z, depending on the set of parameters t, z squared divided by t, plus the sum over tk of z to the power k for k larger equal than 1. Okay, and then yesterday we proved that the tau n can be written as the determinant of m infinity, where m infinity is the semi-infinite extension of the matrix of moments, where the moments are the expectation values, right, of zi is the scalar product z to the power I, z to the power j, where I and j goes from 0 to n minus 1, and this scalar product, so zi, zj explicitly is just the integral over R, the integral over R of z to the power I plus j times rho in the dz. Okay, yeah, and m infinity is just a semi-infinite extension of this matrix, and we said that Mn is a symmetric Hankel matrix. And oh yeah, sure. Oh, no. Sorry. You're right. Yeah. No, this is Mn. This is Mn. And then the Lax matrix. So the Lax matrix is the, so let me write it here. So the, then we consider the semi-infinite extension, the factorization of by lower triangular matrices of m infinity, the semi-infinite extension of Mn, and then we define the Lax operator. So the Lax matrix as S lambda S to the minus 1. Okay, so it's just the notation we introduced yesterday. Okay. Yeah. So lambda is the shift matrix, and then the proof of the theorem, and I followed Adler and Van Moerbeke. So on this proof, we have that L, the matrix L, is actually a lattice matrix for the Toda lattice calculated on a particular solution. So the derivative of L with respect to T is the commutator of 1/2 L to the power K skew symmetric part of the L to the power K commutator commutated with L. Okay, so the matrix L is symmetric and lower and tridiagonal, and you can look at. I use this notation I discovered yesterday, non-canonical. So A1, A2, and so on are the elements on the diagonal of this matrix, and then B1, B2, and so on, B1, B2, and so on are the off-diagonal terms. Yeah, clearly AI and BI are functions of the parameters T, of course. So essentially, now we want to look at the more in details of what this hierarchy of equations looks like and what is the meaning, and how to perform the thermodynamic limit, to look at the thermodynamic limit for the random matrix ensemble by looking at the limit for the Toda lattice where n tends to infinity. What does it mean that the limit of the Toda for the Toda lattice, the limit of Toda lattice where n tends to infinity? This is equivalent to consider the continuum limit of the Toda lattice. Okay, so probably it will be helpful, okay, just to for the sake of completeness, to and help our intuition in terms of the dynamical system interpretation, to specify the so-called Flaschka variables in terms of the natural physical variables. Okay, so just a small digression on the Toda lattice. So the Toda lattice is a Hamiltonian completely integrable system of n particles. So and so on. We have particles on a one-dimensional lattice, a chain, and the Hamiltonian is 1/2, the sum over I running from 1 to n, which can go. You know, the lattice can be infinite. You can consider the chain to be infinite or just finite and impose some periodic boundary conditions, for example. So yi to the power 2 plus, now the part that we care about is sum of, let me move this a bit, exponential of xi minus xi plus 1, right? So essentially we got z, we got x1, x2, x3, and so on. So consider, for example, a semi-infinite lattice, just to fix our ideas about this, and we take n particles, okay, up to xn, whose positions are x given associated to the variable x, and x, the equation of motion. So yi dot is exponential of xi minus 1 minus xi minus exponential of xi minus xi plus 1. Okay, so where I goes from 1 to n. Okay, we stick to the finite dimensional system. So AI is defined as 1 over 2 yi. Okay, it's essentially just the momentum, and BI is 1 over 2 the exponential of 1 over 2 xi minus xi plus 1. Okay, so AI are the elements on the diagonal, are carry information about the momentum, and BI carry information about the relative displacement of the particle. Okay, so but no, yeah, I mean, this is the straight line, but there are no particles on this side. So, okay, so I'm just considering the well. Oh no, that's right. Yeah, minus 1. Yes. So yeah, thank you. No, yes, that's right. Yeah, it should be. All right, Kel. Okay, yeah. So it should be, yeah, from 1 to n minus 1. Yes. So, and yeah, for our purpose. Oh, right. Yeah, that's right. Yes. Yeah, that's right. Yeah, that's right. Yeah, I'm not actually discussing this distinction, because what we need eventually is the semi-infinite extension for the purpose of the thermodynamic limit. So yeah, that's right. So this gives us like an intuition about the correspondence. So essentially, the problem of the unitary ensemble is reduced to the problem of understanding where the eigenvalues are of these matrices, and the eigenvalues of these matrices are associated to the elements of the Toda system, distributed on a one-dimensional on the line, and essentially the problem reduces to a one-dimensional integrable chain, Hamiltonian integrable chain. So now, what is the connection between the elements of this random matrix, of this the Lux matrix, and the tau function? Okay, there is a here we rely on the Toda theory, okay, which tells us how to relate the entries of the matrix L to the tau function. So in particular, AN is the derivative with respect to the time t1, which is interpreted essentially AI dot is the derivative of AI with respect to t1. Okay, t1, the first coupling constant correspond to the physical time in the Toda lattice. The higher times are the times associated to the higher symmetries. And AN is the derivative with respect to T1 of the log of tau n plus 1 divided by tau n, and Bn in this notation is the square root of tau n plus 1 times tau minus tau n minus 1 divided by tau n squared. So these variables, the definition, this connection can be found in different ways. So a simple way to do it, which I'll tell you words. I won't do it in detail, but you can start from the equations for the Toda lattice from the Rota equations for the Toda lattice, so the equations to which the tau function satisfies, and then using this definition, you can derive the equation for the Toda equations for the Toda lattice. So now, given this definition and these notations, let's look at this equation. Okay, the equation for the Toda system, corresponding, for example, to the first time, T1. So what does it look like? In terms of the variables an and bn, so we have the derivative of an with respect to T1 is equal to bn squared minus bn minus 1 squared, and the derivative of bn with respect to T1 is equal to bn divided by 2 times an plus 1 minus an. Okay, so this is for example, the first equation. So you calculate the individual entries of this matrix representation, and for T1, the first equation of the hierarchy is this equation, which is equivalent to the equation of the equations for the Toda lattice, the Hamilton equations for the Toda lattice, perfectly equivalent. But then, for example, what is the next equation in the hierarchy? I want to write it because I want to make a comment on this. Derivative of an with respect to T2 looks like this: an plus 1 bn squared minus an minus 1 plus an times bn minus 1 squared. So, and then the derivative of bn with respect to T2 is equal to bn divided by 2, so bn plus 1 squared minus bn minus 1 squared plus an plus 1 squared minus an squared. Okay? So we see the first equation contains only nearest neighbor interactions, and the second equation of the hierarchy contains next to nearest neighbor interaction, and so on, right? This because L to the power 2, L to the power k gives you a multi-diagonal symmetric matrix, of higher order, and then you involve the couplings between more elements in the chain. Okay? And so this equation is the reason why I'm writing this equation is that I just want to mention this, although it's another chapter of this business which I will not cover today, but I just want to mention it. So imagine that you have your unitary matrix ensemble where the Hamiltonian contains couplings of any order, right? So you have the trace of T1m, right? So the Hamiltonian contains, the Hamiltonian is minus m squared divided by 2 plus the sum of tk, so tk m to the power k, right? So the Hamiltonian that defines the Gibbs distribution is of this form, right? So we formally have interaction terms of any order, right? So, but imagine that instead of considering this model, where you have all interaction of any order, even an odd order, you want to consider a restriction where instead of you want to preserve some symmetry, and you only have even order interactions, only even powers. This means that you have to set T1, in general, 2i plus 1, the times associated to the odd powers equal to 0. Right? So, and then in that case, if you still want to stick to the integrability description, you might ask yourself, okay, if instead of considering this model here, I consider the model where there are no odd order interactions, and this is a real case. For example, in the earlier works on this of Itkinson, Parisi, Zuber, and they consider actually a model with even order interactions only. You might ask, okay, what is the system, the integrable systems associated to that? And then if you look at the Toda lattice by itself, it's not quite clear, because you say, all right, what does that mean? It means that there is no T1. How do I calculate AN? So there is no dependence on that. So the AN, the diagonal, must be equal to 0. But a Toda lattice where the moments are constant equal to 0 and the displacement can change does not make any sense. So what is the reduction? So the reduction is constructed by removing completely the elements of the hierarchy, the times, the odd times, and you preserve the hierarchy with the even order, with the even times only. Okay, so take this hierarchy, you remove the the odd times equations of the hierarchy. You are left with a subset of this hierarchy, and in that hierarchy you set the diagonal, equal to 0. And you may wonder, what do you get? So this equation is just discarded, and what you left is this equation and the even times analogs, and the other even times analogs. So, and then if you do this, you take the even times analogs and you set A equal to 0, you get a consistent hierarchy. And what is this? This is the Volterra lattice. So the first equation, you get the equation for Bn, so let me write it. I need to introduce a notation. So capital B, where capital Bn is just small bn squared. Okay, so the equation, these equations reduce to a single equation for Bn, capital Bn, defined as the square of Bn. Okay, so, and this is the system that actually Volterra wrote in his I think 1926 work to describe the population dynamics. Okay, and later on was discovered to be completely Hamiltonian and integrable. So, so this is to say that the reductions, the problem of the reduction requires some attention, because there's this step of discarding half of the hierarchy and then perform a consistent reduction of the system. And so the Volterra equation is also, some people refer to it as the discrete KdV, and people study the continuum limit in relation to, for example, the problem originally set by Witten and Kontsevich. So All right, let's go back to our main business. So we got a system of equations, okay, the Toda system, these equations, all the other equations. But as we mentioned, the tau function is a particular solution. And if we want to specify this particular solution through a system of differential equations, we need to fix the initial condition if we want to be hopeful to be able to specify the solution. So the first question is, what is the initial condition associated to this system that specifies this the solution, the tau function we're looking for. So first, let's look at what the tau function is for if you set all the t's equal to 0, all the times, or if you wish, the couplings equal to 0. What we have is just the integral over Rn of the van der Monde determinant squared, right? And then we got the product for I running from 1 to n, the exponential of minus zi squared divided by 2 dzi. Okay? So this corresponds, this is the partition function for the Gaussian unitary ensemble. Right? So with the Gaussian measure, so this means that the problem of finding, once we have the differential identities, that in this case is called the Toda system, the problem of the specifying the initial condition is a simpler problem, because you have to know, you need to know the Gaussian unitary ensemble, for which many results are available. Okay? In particular, this integral can be calculated explicitly using the Selberg's theorem. So you can find, I guess, all the versions of Selberg's theorem in Meta's book. So I'll refer you to that. Meta's book on random matrices, and if you struggle to point the right one, so I can tell you the page, and so and the exact point in the book where you can find it. In particular, what we're interested in is the integral over Rn of the van der Monde determinant to the power 2 gamma in modulus. So the product for I running from 1 to n of the exponential of minus a zi squared in zi. And and this is 2 pi over n by 2, and then you get 2a to the power minus n. So let me call this a alpha, okay, just to avoid any confusion with our variables. So alpha minus n gamma n minus 1 plus 1 divided by 2, and then we have the product of gamma 1 plus I gamma divided by gamma of so capital gamma is the Euler gamma function, okay? Small gamma is just a parameter. Alpha is just a parameter. Okay, so here I use the Selberg's theorem in this particular form, which corresponds to the case we are interested in. So So our case, I write here, our case is gamma equal to 1 and alpha equal to 1 over 2. Okay? So this gives us tau n of 0 equal to 1 over n factorial 2 pi n over 2, the product of I over I of I factorial. Okay? So if we just, hopefully I did the calculations carefully enough, we get this explicit expression for the tau function calculated for the free theory. Okay? No interactions, just the, and given this expression, we can calculate what we need, right? So we can calculate Bn, okay, defined as the square root of tau n calculated at 0, okay, divided by tau n calculated at 0 squared. And then if we carefully do the substitutions, so we find that Bn is just the square root of n. Okay, so this is the initial condition on the off-diagonal elements of the Lax matrix L. So, and as far as An is concerned, so the problem is actually simpler. We don't need any Selberg's theorem, because we just observed that the calculation of An involves the calculation of the derivative with respect to T1, okay, of the tau n. But the measure of integration is even. If you differentiate with respect to T1, we drag in front of the exponential an odd, just a monomial z, a sum of z, of variable zi's. And this is an odd function, so the integral will be equal to 0, right? So over all Rn. Okay, so it follows just from the symmetries of the argument. There is no, we don't need anything else. So this is, okay, I need to be a bit more precise. This is this is the initial condition on the Lax matrix. So, at this point, we got everything we need to look at the thermodynamic limit, okay, the continuum, which will correspond to the continuum limit of the Toda lattice, okay? What happens if n tends to infinity? In order to do this, we first need to specify a scale. So specify a scale, which I call capital N, and then the regime we're interested in is the regime where small n divided by capital N is of order 1 when both tend to infinity. Okay, so this is how we set up the thermodynamic limit. So we fix a scale, we introduce a parameter capital N, which is meant to be large, and then the regime we look at is the regime of n, small n, which are comparable, of the same order of capital N. How do we use this scale? So we introduce this scale to rescale the variables at play in the partition function. So we got, what are these variables? We got zi, and then in order to not to overcomplicate the notation, instead of redefine the zi, I will replace it with its rescaled version, square root of n zi. Okay, so I replace in my formulas, okay, in my formula for the tau function, I will replace Zi with square root of n Zi. And also I need to redefine or introduce this scale in my independent variables, the t. So tk, okay, is replaced with tk divided by n to the power k over 2 minus k over 2 minus 1. Okay. Just want to mention that this rescaling is quite natural. For example, if you just look at the GUE, the Gaussian unitary ensemble, okay, where we essentially kill all the times, T1, T2, and so on, what the famous result of Wigner is that if you look at the rescaled distribution of the rescaled, the distribution of the rescaled eigenvalues, okay, the rescaled ones, rescaled eigenvalues, the probability distribution of the rescaled eigenvalues in the continuum in the limit for large n for n infinity is the famous semicircular law. Okay, so the probability distribution is okay. It doesn't quite look like a semicircle, but my drawing is not the best. So yeah, should be a bit more like this. And so the semicircular law. So and this is necessary because otherwise, you know, the magnitude of the eigenvalues would just go to infinity as we increase the size of the matrices. Okay, in the right scaling, in order to find this compact support, is the square root of n. Okay, this is how the rescales, and we essentially I'm using the same rescaling that you would require in absence of interactions. So what do we need to do now is to implement just this notation. So I will write the result. So after the rescaling, the tau function Tn of t will read as 1 over n factorial, the square root of n to the power n squared. Let me write the result. So 1 over n factorial, square root of n to the power n squared, the integral over Rn of delta n squared, the Vandermonde, and then the exponential, the product of the exponentials. So minus Zi squared over 2 plus the sum over tk Zi to the power k in dZi. Okay, so then what we need to do, the limit, the behavior of this integral and all related observables in the large n limit has to do with the asymptotic evaluation of this integral. And of course the behavior will depend on what kind of regime we're looking at. Okay, and then this will be clearer in a moment. So what I want to do is to introduce a parameter. So the beloved parameter epsilon, and we define x as small n over capital N, so epsilon n. And then let's first look at what happens to the initial condition. Okay, what is the initial condition? Bn of 0 is the square root of n, as we said. So this is the square root of x divided by the square root of epsilon. So we see that after this rescaling, this is important because somehow the initial condition gives us insights about the right scaling we need to apply to the dependent variables. So we see that Bn depends explicitly on the square root of epsilon. So this suggests that the variable I need to consider is the square root of epsilon times Bn equal to the square root of x. So this variable, this indicates that for this variable, it would make sense to consider an expansion in epsilon where the leading order is order 0 in epsilon, and then we have higher order corrections in epsilon. And so given this observation, what we define, we introduce the interpolating functions. So the interpolating functions are defined as, so u function of x and the times t equal to the square root of epsilon Bn function of t, and the v is x t equal to the square root of epsilon an function of t. Okay, I define these interpolating functions where essentially if x is equal to small n over capital N, I reproduce the actual variables Bn and An. Okay, and but I can extend it to any other value of x. And also, what do we have? So the rule is that u of x plus or minus epsilon. Okay, if we shift x, we get the square root of epsilon b of n plus minus 1 function of t, and then v function of x plus minus epsilon is similarly the square root of epsilon a n plus minus 1 the square root of t. Of course, in the consideration about the rescaling, I don't look at a because it's, the initial condition is identically 0, is already independent on epsilon. Okay, so for example, let's look at the first equation of the hierarchy. Okay, we see what happens under these notations. So this what do we get for example, when the time t1, when you do the rescaling, becomes t1 divided by n to the power minus 1 over 2, okay, using the definition, which is t1 divided by the square root of epsilon. So in the equations for the Toda, the first equation for the Toda lattice, which perhaps I can just copy again. So dan t1 bn squared minus bn minus 1 squared, and dbn t1 equal to bn over 2 an plus 1 minus an. So with this substitution, just gives us the derivative of v with respect to t1 is equal to u squared x minus u squared of x minus epsilon divided by epsilon, and du by t1 is u times v of x plus epsilon minus vx divided by 2 epsilon. Okay? So where here I omitted the dependence on the times t just for shortness. Okay? Of course, all the u and v's depend on all the t's, okay? Including, of course, t1s. So, okay, now we got set up to perform the continuum limit. So epsilon, if epsilon tends to 0, so continuum stroke thermodynamic so the continuum stroke thermodynamic limit corresponds to studying the regime where epsilon tends to 0, right? So this epsilon tends to 0. So capital N tends to infinity, and therefore small n, we're looking at the case where small n tend to infinity. So expanding, what we can do on the right-hand side here is to expand in Taylor series u of x minus epsilon, v of x plus epsilon, and then let's see what we get. So expanding in Taylor series, so what do we get is dv by t1 is equal to 2 times ux minus, I write just the first term for this, the purpose of this lecture, times epsilon, okay, let me write another one. So 1 over epsilon, 1 over 3 u xxx plus ux u double x epsilon squared plus higher order terms, and du by t1 is equal to 1 over 2 u times vx plus 1 over 4 u times vxx epsilon plus 1 over 12 u v triple x epsilon squared plus higher order corrections. And so this is interesting. So if, for example, we assume that epsilon is equal, you just brutally discard the higher order corrections, assuming that, although we don't know a priori, that you can control the series, the higher order correction. Suppose they are finite, you can safely send epsilon to 0. What we left is this system here, which is called the dispersionless Toda lattice equation. So this is a quasi-linear system of hydrodynamic type, and it is completely integrable by linearization, essentially, by the Hodograph method. I will spend essentially the rest of the time we've got on this aspect. But before we move on, let's look at the corrections. So we see that we have the first order correction in epsilon contains second derivatives. So even order derivatives, or the first order derivatives with a weight 2, with a to a power 2. Okay, so the weighting in x is 2, and this characterizes typically the viscous system. But I hold on this for a moment. So the next correction shows us a third derivatives, and we see that there is a term that is not quite, but is similar to the KdV. So we have uxx, but we have a factor u, which, you know, makes a difference. Well, the similarity with the kV stays in the fact that this term introduces a dispersive correction rather than dissipative. So what is the difference between dispersive and dissipative? So dispersive means that if you linearize the equation, okay, so we perturb around the constant solution, you linearize the equation, and you look at the dispersion relation. The dispersion relation is real valued, and this denotes the dispersive, marks the dispersive character of the equation. If you take instead, if you have an even order correction, and you linearize it and look at the dispersion relation is complex valued, and this means that there is the system is dissipative. Okay, so there is a loss of energy in the system. So the important thing, the fact that we have the term of comparison I'm considering, probably I open a parenthesis here. So is the case where, would be the case where U, for example, satisfies, so this equation here, that is the Burger's equation. Okay, so this is the equation we obtained in the first lecture, satisfied by the magnetization for the spin, the mean field spin system. So the mean field spin magnetization satisfies the Burger's equation, so a dissipative equation. And as we learned, okay, as we know, the shock, so this equation for a small epsilon develops a gradient catastrophe, and this correction here regularizes the catastrophe by introducing a sharp transition from the behavior on the left-hand side and the behavior on the right-hand side. So at higher time, essentially, this correction removes the multivaluedness and replaces the multivaluedness with a sharp transition from the asymptotic behavior on the left and the asymptotic behavior on the right. So if instead you replace, instead of having a viscous regularization, a term with a second order derivative, okay, for the sake of simplicity, and imagine you have KdV, okay, you add the derivative here, you have a correction of this type, okay, of order epsilon squared. Suppose there is no viscosity, no second order derivative. What happens when the initial condition evolves and develops a gradient catastrophe? What is the effect of this correction? The effect of this correction is the system is Hamiltonian, has to preserve all the conserved quantities across the singularity, and this induces oscillations that in time evolve in a fan of oscillations connecting. So yeah, the behavior is a bit more, should probably do something a bit nicer. So you would have a gradient catastrophe, and then beyond the gradient catastrophe, you would have oscillations connecting the two asymptotic behaviors on the left and the right. So these oscillations, the number of oscillations increases, you get this expanding fan that increases and occupies more and more space in the x direction as time evolves. Okay, this this mechanism is a different regularization mechanism and has a name. So the previous one was called the classical shock. This is called a dispersive shock. It's what is called a dispersive shock wave. And it was discovered by Gurevich and Pitayevsky in 1974 in the context of the KdV equation to describe shock waves in plasma.